Welcome back. In the last video, I issued the challenge of trying out torch.squeeze, which removes all single dimensions from a target tensor. And how would you try that out? Well, here's what I would have done. I'd go to torch.squeeze and see what happens. Open up the documentation, squeeze, input dimension, returns a tensor with all the dimensions of input size 1 removed. And does it have some demonstrations? Yes, it does. Wow. Okay. So you could copy this in straight into a notebook, copy it here. But what I'd actually encourage you to do quite often is, if you're looking up a new torch method you haven't used, code all of the example by hand, and then just practice what the inputs and outputs look like. So X is the input here. Check the size of X, squeeze X, well, set the squeeze of X to Y, check the size of Y. So let's replicate something similar to this. We'll go into here, we'll look at X reshaped, and we'll remind ourselves of X reshaped.shape. And then how about we see what X reshaped.squeeze looks like? Okay. What happened here? Well, we started with 2 square brackets. And we started with a shape of 1, 9, and removes all single dimensions from a target tensor. And now if we call the squeeze method on X reshaped, we only have 1 square bracket here. So what do you think the shape of X reshaped.squeeze is going to be? We'll check the shape here. It's just 9. So that's the squeeze method. Removes all single dimensions. If we had 1, 1, 9, it would remove all of the 1s. So it would just end up being 9 as well. Now let's write some print statements so we can have a little pretty output. So previous tensor. This is what I like to do. This is a form of visualize, visualize, visualize. If I'm trying to get my head around something, I print out each successive change to see what's happening. That way, I can go, oh, okay, so that's what it was there, and then I called that line of code there. Yes, it's a bit tedious, but you do this half a dozen times, a fair few times. I mean, I still do it a lot of the time, even though I've written thousands of lines of machine learning code. But it starts to become instinct after a while. You start to go, oh, okay, I've got a dimension mismatch on my tensors, so I need to squeeze them before I put them into a certain function. For a little while, but with practice, just like riding a bike, right? That trite saying, it's like when you first start, you're all wobbly all over the place, having to look up the documentation. Not that there's much documentation for riding a bike, you just kind of keep trying it. But that's the style of coding I'd like you to adopt, is to just try it first. Then if you're stuck, go to the documentation, look something up, print it out like this, what we're doing, quite cumbersome, but this is going to give us a good explanation for what's happening. Here's our previous tensor, X reshaped, and then if we look at the shape of X reshaped, it's 1, 9. And then if we call the squeeze method, which removes all single dimensions from a target tensor, we have the new tensor, which has 1 square bracket removed, and the new shape is all single dimensions removed. So it's still the original values, but just a different dimension. Now let's do the same as what we've done here with unsqueeze. So we've given our tensors a hug and squeezed out all the single dimensions of them. Now we're going to unsqueeze them. We're going to take a step back and let them grow a bit. So torch unsqueeze adds a single dimension to a target tensor at a specific dimension. Now that's another thing to note in PyTorch. Whenever it says dim, that's dimension, as in this is the 0th dimension, 1st dimension, and if there was more here, we'd go 2, 3, 4, 5, 6, etc. Because why? Tensors can have unlimited dimensions. So let's go previous target can be X squeezed. So we'll get the squeezed version of our tensor, which is X squeezed up here. And then we'll go print the previous shape is going to be X squeezed dot shape. And then we're going to add an extra dimension with unsqueeze. Then we go X unsqueezed equals X squeezed, so our tensor before that we removed the single dimension, and we're going to put in unsqueeze dim, we'll do it on the 0th dimension, and I want you to have a think about what this is going to output, even before we run the code. Just think about, because we've added an extra dimension on the 0th dimension, what's the new shape of the unsqueezed tensor going to be? So we're going to go x unsqueezed, and then we're going to go print. We'll get our new tensor shape, which is going to be x unsqueezed dot shape. All right, let's have a look. There we go. So there's our previous tensor, which is the squeezed version, just as a single dimension here. And then we have our new tensor, which with the unsqueezed method on dimension 0, we've added a square bracket on the 0th dimension, which is this one here. Now, what do you think is going to happen if I change this to 1? Where's the single dimension going to be added? Let's have a look. So instead of adding the single dimension on the 0th dimension, we've added it on the 1st dimension here. It's quite confusing because Python is 0th index, so I kind of want to, my brain's telling me to say first, but it's really the 0th index here, or the 0th dimension. Now let's change this back to 0, but that's just another way of exploring things. Every time there's like a parameter that we have here, dim equals something like that, could be shape, could be size, whatever, try changing the values. That's what I'd encourage you to do. And even write some print code like we've done here. Now, there's one more we want to try out, and that's permute. So torch.permute rearranges the dimensions of a target tensor in a specified order. So if we wanted to check out, let's get rid of some of these extra tabs. Torch.permute. Let's have a look. This one took me a little bit of practice to get used to. Because again, working with 0th dimensions, even though it seems like the first one. So returns a view. Okay, so we know that a view shares the memory of the original input tensor with its dimensions permuted. So permuted for me, I didn't really know what that word meant. I just have mapped in my own memory that permute means rearrange dimensions. So the example here is we start with a random tensor, we check the size, and then we'd have torch permute. We're going to swap the order of the dimensions. So the 2nd dimension is first, the 0th dimension is in the middle, and the 1st dimension is here. So these are dimension values. So if we have torch rand n 235, 201 has changed this one to be over here, and then 01 is 23, and now 23 there. So let's try something similar to this. So one of the common places you'll be using permute, or you might see permute being used, is with images. So there's a specific data format we've kind of seen a little bit before, not too much. Original equals torch.rand, size equals, so an image tensor, we could go height, width, color channels on the end. So I'll just write this down. So this is height, width, color channels. Remember, much of, and I'm going to spell color Australian style, much of deep learning is turning your data into numerical representations. And this is quite common numerical representation of image data. You have a tensor dimension for the height, a tensor dimension for the width, and a tensor dimension for the color channels, which is red, green, and blue, because a certain number of red, green, and blue creates almost any color. Now, if we wanted to permute this, so permute the original tensor to rearrange the axis or dimension. Axis or dimension are kind of used in the same light for tensors, or dim order. So let's switch the color channels to be the 1st or the 0th dimension. So instead of height, width, color channels, it'll be color channels, height, width. How would we do that with permute? Let's give it a shot. X permuted equals X original dot permute. And we're going to take the 2nd dimension because this takes a series of dims here. So the 2nd dimension is color channels. Remember 0, 1, 2. So 2, we want 2 first, then we want the height, which is a 0, and then we want the width, which is 1. And now let's do this. Shifts axis 0 to 1, 1 to 2, and 2 to 0. So this is the order as well. This 2 maps to 0. This 0 maps to the first index. This 1 maps to this index. But that's enough talk about it. Let's see what it looks like. So print previous shape, x original dot shape, and then we go here, print new shape. This will be the permuted version. We want x permuted dot shape. Let's see what this looks like. Wonderful. This is exactly what we wanted. So you see, let's just write a little note here. Now this is color channels, height, width. So the same data is going to be in both of these tensors. So x original, x permuted. It's just viewed from a different point of view. Because remember, a permute is a view. And what did we discuss? A view shares the same memory as the original tensor. So x permuted will share the same place in memory as x original, even though it's from a different shape. So a little challenge before we move on to the next video for you, or before you move on to the next video, try change one of the values in x original. Have a look at x original and see if that same value, it could be, let's get one of this 0, 0, get all of the dimensions here, 0, see what that is. Or can we get a single value maybe? Oops. Oh, no, we'll need a 0 here. Getting some practice on indexing here. Oh, 0, 0, 0. There we go. Okay, so maybe we set that to some value, whatever you choose, and see if that changes in x permuted. So give that a shot, and I'll see you in the next video.